Hello students, this is continuation topic for Tautomerism part 4, and now I am going to explain mechanism of keto-enol tautomerism, and also I will discuss important questions on tautomerism, right? So generally keto-enol tautomerism is involved under two types of catalyst. One is acid catalyst and another one is base catalyst. Right, now I am going to give mechanism of acid catalyzed reactions of keto-enol tautomerism. Right, acid catalyzing mechanism. So now I am going to take a simple compound that is simple aldehyde, acetaldehyde. So the name of this compound acetaldehyde. Right, acetaldehyde. So, and is only one aldehyde, sir. Here now it is carbonyl compound. So in this carbonyl compound, C double bond O group is keto group. That's why this is keto form. Right, this is keto form. Now this is alpha carbon, sir. Because carbonyl compound, next carbon is called alpha carbon, which has 3 hydrogens. That's why these 3 hydrogens are called alpha hydrogens. Total we have 3 alpha hydrogens. That's why this is involved in keto-enol tautomerism. Right, what is the mechanism here? You know what, here this C double bond O group, oxygen is more electronegative atom. Here oxygen always contain 2 lone pairs. Right, oxygen always contain 2 lone pairs. I told you already this is under H plus acid catalyst. Here H plus is proton, now it is act as a catalyst. Right, so now this one of the lone pair is attracted towards proton, and now this lone pair will make a bond between oxygen to hydrogen. That's why the right of the next step, CH3 double bond CH3 bond double bond oxygen. Oxygen now has only one lone pair lost, and to form OH, right, and bond H. What happened here? So one of the here one of the pi bond is shifted towards its positive charge. Now oxygen get its lone pair. So write down the next step here. CH3 single bond hits lone pair, retain its lone pair OH. Now carbon get positive charge here. Right, carbon get positive charge. I told you already here this is alpha carbon, sir. We have 3 alpha hydrogens are there. Right, we have 3 alpha hydrogens are there. I want to use 1 alpha hydrogen initially. Right, this is one of the alpha hydrogen. So we know that. So bond here break. Now hydrogen get positive charge. This bond rotate between these 2 carbon. Right. So the next product will be, next step here, CH2 double bond OH bond H. You know what, here H plus is eliminated. Right, here carbon to carbon double bond, that's why this is one alcohol, suffix is enol. Now this is enol form. So keto-enol tautomerism. So this is the mechanism of acid catalyzed mechanism of keto-enol tautomerism. Here you need to understand here end of the reaction. Here end of the reaction H plus is eliminated. In this end of the reaction H plus is eliminated. Why? Because here H plus is act as only catalyst. So what is the definition for catalyst? It is which is increase the rate of reaction and which is move towards forward reaction, but not do not disturb the formation of product. That's why here H plus is involved in this reaction, and end of the reaction H plus must be eliminated. So that's why this is under H plus, acid catalyst reaction. Right, now base catalyst reaction, base catalyzed reaction. Now base catalyzed mechanism. Base catalyzed mechanism. So here what is the mechanism here? Same, I want to take here simple molecule, same molecule, acetaldehyde. I told you already this is alpha carbon, sir. I want to use initially 1 alpha hydrogen here. So base here, what is the base? OH minus is base here. So base is attractive towards this proton. Right, immediately this bond will break. Now this hydrogen get positive. So OH minus plus H plus to form here H2O, right? To form here H2O. Now this bond rotate towards between these two carbon. Immediately this bond rotate towards oxygen. Now oxygen gets negative charge. Now the next step is CH2 double bond CH bond O minus bond H. Now this is enolate ion, right? This is enolate ion because oxygen has negative charge, carbon to carbon double bond. That's why it is enolate ion. Now here this H2O again is involved in this reaction. Of course we know that H2O structure is bent structure, right? H2O. Now here bond here breaks up because oxygen is negative charge. Immediately this is attract toward this proton. Now hydrogen get positive charge. Now this bond rotate towards oxygen. So here OH minus is eliminated, right? The next step is CH2 double bond OH bond H. Now it is also enol form. Now this is keto form, right? This is keto form. That's why it is also keto enol tautomerism. But this keto enol tautomer is under base, is completed through base mechanism. It is completed through acid catalyst, right? So this is base catalyst reaction and this is acid catalyst reaction. So this is the mechanism of keto enol tautomerism, in which one is acid catalyzed mechanism and second one is base catalyzed mechanism, right? So I hope all of you understand here, right? So now we are going to discuss important questions on keto enol tautomerism, right? And exhibit tautomerism, right? So the first option, let us go for discuss about the first question. Here this is aldehyde. Now CHO is aldehyde here. Aldehyde is carbonyl compound in which C double bond O group is attached to an sp3 carbon. That is the first tool to exhibit tautomerism, right? So write down the structure for an aldehyde, right? C double bond OH, right? C double bond O group is attached to an sp3 carbon. Now C6H5, nothing but benzene ring. So benzene ring is not a sp3 carbon. Yes or no? Write down the structure for benzene, right? So double, single, double. Yes, here this is a benzene ring, sir. This C double bond O group is attached to and these carbons are, right? This carbon is carbon to carbon double bond, sir. That's why this is not a saturated carbon and this is double bond carbon. That's why it is exhibit sp2 hybridization, right? sp2 carbon. That's why this is benzaldehyde. What is the name of this compound? Benzaldehyde will not show or will not exhibit tautomerism. The next, go for the next carbon. Go for the next option. Here also benzene rings are C6H5. That's why this benzene ring will not exhibit tautomerism because all carbons in benzene ring sp2 hybridized carbon. That's why, so this is not possible. Of course here keto form is carbonyl compound. Next carbon, here carbon Me3, nothing but Me is for CH3 group, right? One Me is equal to one CH3, methyl. Me nothing but here methyl. So methyl formula CH3. Here how many methyl we have? Generally 3 methyls are there, right? 3 methyls are there. Write down 3 methyls here. 1 CH3, CH3 and CH3. Total 3 CH3 are there. Of course here this is saturated carbon. 1, 2, 3, 4. Of course here this is saturated carbon. And this act as sp3 carbon. But here no alpha hydrogens are there, sir. No alpha hydrogen. That's why, so second option also will not show and will not exhibit tautomerism. And coming into third option, right? What about third option? Yes, this is carbonyl compound, keto group. Now this C6H5 benzene ring, sir. That's why this carbon of benzene ring will not show, will not exhibit tautomerism. Of course here two carbonyl compounds are there. Of course this is now it is also act as alpha carbon. Now this alpha carbon has 2 alpha hydrogens and it is sp3 carbon. That's why, so this is sp3 carbon. That's why this third option will exhibit tautomerism. Of course coming into fourth option keto forms are carbonyl compound. Here also C6H5, it is also C6H5. 2 phenyl rings are there. That means 2 benzene rings are there. That's why the fourth option also here will not exhibit tautomerism because here benzene ring is all carbons are an sp2 hybridized carbon. That's why will not exhibit tautomerism. Only third option will exhibit tautomerism. Next, coming into the second question, which of the following will not show tautomerism? Will not show tautomerism. Of course, it is bicyclic compound, monocyclic compound, and monocyclic compound. We have the four options. First option is bicyclic compound. So this is carbonyl compound, sir, in which C double bond O group is attached to an sp3 carbon. Of course, this is also sp3 carbon and it is also sp3 carbon. I told you already, bridge heads, right? Bridge heads carbon, so will not exhibit tautomerism because bridge head carbon will get more steric strain due to the carbon to carbon double bond, and also when you remove this alpha hydrogen, what happens are here bridge will break, right? So cannot be planar and due to steric strain, and if you remove alpha carbon from this bridge head of carbon, bridge will break, right? So, and this is sp3 carbon, sir. This is sp3 carbon, right? It is sp3 carbon, and also here sp3 carbon and cyclic carbon. Now it is not a bridge carbon, so that's why here two hydrogens are sufficiently to involve in keto-enol tautomerism. That's the first option is possible. And coming into second option, sir. So I hope second option is correct answer. Will not exhibit, right? Or will not show keto-enol tautomerism. Here this is carbonyl compound, sir. This is carbonyl compound in which, so this is bridge head, right? Bridge head, I told you already, bridge head will not exhibit tautomerism. Will not exhibit tautomerism. And this is sp3 carbon, sir. But here this is a saturated carbon and sp3 carbon. But here no alpha hydrogens are there. That's why it is also will not. This is will not exhibit tautomerism. I hope this is the correct answer. Of course, coming into third option, here two ketones are there, sir. It is also alpha carbon. It is also alpha carbon, and it is saturated carbon. It is saturated carbon. So that's why it is possible, and it is involved in keto-enol tautomerism. Of course, fourth option, it is also diketones are here. It is alpha carbon. With respect to it is also alpha carbon. It is also alpha carbon. All alpha carbons are saturated carbons. That's why, and sp3 carbon. That's why it is also exhibit keto-enol tautomerism. Only second option here will not exhibit keto-enol tautomerism.
Right. Third question: stability order among these compounds, among these tautomers. Stability order among these tautomers. Right. See, these all are bicyclic compounds, sir. Right. Here X is keto form, X2 form, Y-enol form, and Z-enol form also. Among these three tautomers, which one is more stable? If you find more stable of compound, definitely, you are going to take a correct answer because all are decreasing order only. That's why you need to find more stable compound. So that is answer only, right? So I want to explain. So with our mechanism, right? This is keto form, sir, of bicyclic compound. So keto form. Right. Here this keto form, the next carbon is alpha carbon. Here also next carbon is alpha carbon. We have two alpha carbons are there. So initially I want to use one alpha carbon of this bridge head. It is also one of the alpha carbon of two hydrogens are there. Bond break here, carbon to hydrogen. Now this bond rotate between these two carbon. This hydrogen get positive charge. This bond rotate towards oxygen and oxygen get negative charge here. This proton towards oxygen to form double bond appear here, OH, right? So this is Z form, sir. Z form of enol, right? This is Z enol form, and I want to use this carbon of alpha hydrogen right now. Bond here break. This bond rotate between these two carbon, and this hydrogen get positive charge here, and this hydrogen also rotate towards oxygen, so to form double bond appear here, OH. This is Y-enol form. According to our question, this is Z-enol form and this is Y-enol form. Coming into which is more stable, sir? Of course, obviously ketone is more stable than enol form. These two are Y and Z enol form. Why? Because it is simple ketones, sir. I told you already, in simple ketones, carbon to carbon double bond C double bond O, bond dissociation energy is more than this carbon to carbon double bond of enol forms. And that is the one reason. And one second reason, sigma bond and this is pi bond, sir. Sigma bond, pi bond, sigma bond and pi bond. So this pi bond of C double bond O of bond strength is more than this pi bond of enol form. That's why, so bond strength of pi bond of C double bond O is more stable than this pi bond of bond strength of enol form. Second reason. But first reason, bond dissociation is more in ketone form. Bond dissociation energy and bond strength also is more in C double bond O of pi bond. So these two reasons are to explain why keto form is more stable in this compound, right? So what are the next stable compounds are? Of course, obviously Y, because YZ is least stable. Of course, it is negligible. It is not possible. Why? Because here this is bridge-head carbons, because these are bicyclic compound. In this bridge-head carbon of this alpha hydrogen, what happens if you remove this alpha hydrogen? Your first reason is bridge will break, and also here keto form, in enol form carbon to carbon get double bonds, sir. That's why this carbon get sp2 hybridized carbon. sp2 hybridized carbon means planar structure and 120 bond bond angle is 120 degrees there. So here planar cannot be possible due to more steric strain according to Brett's rule. And also if you remove this alpha hydrogen, what happens? A bridge will break. That's why these two reasons are to explain bicyclic compound of bridge-head carbon do not involved in tautomerism. That's why, so this is least stable, right? This is second stable. That's why for what is the first one more stable? Keto form. Keto form symbol according to question X. X is the most stable. Then the next stable compound Y. So Y is the most stable. Then what is the least stable compound here? Z. So X greater than Y greater than Z. X greater than Y greater than Z. So that's the first option is correct one, right? So this is the way to bring correct option in bicyclic compounds.
So my dear students, so please watch total 5 parts of tautomerism. If you watch these total 5 parts of tautomerism, definitely you will be able to understand what is the full concept of tautomerism, and definitely you will do any kind of question in competitive exams. So please watch, please subscribe my channel. Thank you.